So these three laws with an appropriate equations are required. For that, in the case of conservation of mass principle, we have to develop equation for continuity equation. Conservation of momentum, from that we develop the Newton's second law. Applying that, we have to find the momentum equation. And from the conservation of energy, we develop the Bernoulli's equation. So that are mathematical aspects. So you are expected to look at your mathematics back, because different mathematical aspects are there. Anyways, in the case of conservation of momentum, conservation of mass, mass is fundamental, that it is the inertial property of substance, okay? And the fundamental concept in analyzing fluid flow, and is expressed through mathematical equations that ensure mass continuity. So its application is there in the combustion chamber. Actually, in the combustion chamber, the hot gases, which are the fuel and oxidizer, mixed together in the combustion chamber and burn to an appropriate ratio. And then this hot gas comes through the narrow section of the exhaust. And due to that, the momentum will happen. So the mass flow rate is related with the amount of fuel consumed per second, or the amount of the exhaust gas that comes through the exit. So that we can develop it. So the law of conservation of mass, or principle of mass conservation, states that for any system closed to all transfer of matter, the mass of the system must remain constant over time. Okay, so that it can be converted. So the law of conservation of mass can be expressed in differential form. So this is a differential form of continuity equation. D rho dt plus the divergence of rho v. So v is velocity, rho is density here. So this equation is just a representative equation for the continuity equation. So density, time, and velocity are the fundamental quantities which we consider here. In the case of conservation of momentum, total momentum for a closed system remains constant in the absence of external force. That is the statement. So this law is very crucial for understanding the force acting on the aircraft in motion. So it implies momentum P is mass times velocity. It is product of mass and velocity. Okay, so the thrust and the drag are also related with that. So the thrust force T is equals to mass flow rate m dot times the exit velocity, as we have discussed in somewhere. Let me simply write it. Okay. So thrust force T is equals to the mass flow rate m dot of the gas times V exit plus pressure of the exit pressure minus atmospheric pressure, the whole times exit area of the engine. So this part is called the momentum thrust part. So momentum plays vital roles in the thrust production. And the remaining is pressure thrust part. This is called pressure thrust part. So we give emphasis for the momentum, that is mass times velocity. And here this is mass flow times velocity, exit velocity. So in the one-dimensional steady flow, how we can represent the momentum equation? Let x is the distance, u is velocity, a is acceleration, t is time, and m is mass. on that. Density rho is given, area A is there, pressure P is given, U, B, so every quantities are there. So from point 1 to point 2, if you take U at point 1 is U plus du dx dx. That is the, and P at point 1 is represented in the second point, P. You can take differential distance, dx. Dx is from here to here, dx. Okay, so yeah, this distance is dx from here to here. Dx differential distance there. So there is a change in pressure here, and there is a change in velocity here. So force is equal to mass times acceleration, simple from the Newton's second law, which is equal to mass times delta U over delta T. So delta U is change in speed or change in velocity or change in time. So that gives you the momentum equation. And the force F is pressure times area with minus sign. Okay, pressure times area 2 minus pressure times area 1. Okay, which is equal to mass times change in velocity over change in time. So just taking the minus sign, overall minus sign and the P, so P plus delta P over delta X. So this component is taken like that, and the area will come out. So P plus delta P delta X times area minus PA, which is equals to these quantities. So finally, what we can get the differential form of equation in one-dimensional, actually. This is for the one-dimensional, along U direction only. This is not for three-dimensional. Only the flow in the one direction. So that's why it is still in one-dimensional flow. So dp dx minus of dp dx is equal to rho u du dx is the differential form of equation. This is a differential form of equation of the momentum. So momentum in one dimension. Another is energy conservation principle. So that the law of conservation of energy states that the total energy of an isolated system remains constant. And it says the energy to be said to conserved over time. So in this case, we may consider closed system and open system also. The closed system, the ideal closed system, the energy at the initial point is equals to energy at the final. Okay, energy at the initial means maybe potential energy plus kinetic energy at the initial point is equal to potential energy plus kinetic energy at the final. So that is maybe mgh plus half rho, half mv square, which is equal to half mgh h final plus half mv square final. So this is just in the closed system. So in the closed system, in the open system, the initial energy, total initial energy, is equals to final energy plus some heat and other energy losses, because there are some losses in the process in the case of open system. But in the closed system, it is just within the confined state, so that there is no loss is considered. It is ideal condition. So, for example, this is the thermodynamics law of the flight vehicle within the combustion chamber. So, this is just an engine of aircraft. So, there is point 1 and the point 2. So, through this point 1 and the point 2, we have a relation of internal energy, enthalpy, heat flow, and the kinetic energy and the pressure. So what it states, the work done, which is equals to P2 V2 minus P1 V1 plus shaft work. You can see this is a shaft work. This equation tells us that the total work done is equals to P2 V2 minus P1 V1, because 1.1 is the inlet condition, point 1 inlet, point 2 maybe exit. And we have a shaft that transmits power. Okay, so P2 V2 minus P1 V1 plus shaft work, which is equal to the total work. And then we can bring this to some thermodynamic equation. The internal energy E2 minus E1 plus K2 minus K1, which is equals to Q times shaft work minus P2 V2 plus P1 V1. So just relating the work done with the kinetic energy and internal energy. So finally, mathematically, what we can get from this is the total enthalpy. The change in enthalpy is equals to change in enthalpy is equals to Q, that Q is heat flow minus shaft work. So this is the conservation of energy principle. So now let's come to the formulation of continuity equation, how we can formulate. We already discussed about the continuity equation or the mass flow equation. Actually, this continuity equation is in differential form, but let me put it in the form of m dot mass flow rate m dot is equals to rho density rho times area A times velocity V. So, which is equals to constant. That is the meaning of constant. I can say simply C, or constant, you can say. This is called the continuity law. So the mass flow rate, which is equal to density of the fluid, area of the given cross-section times the flow velocity. So this is called a continuity equation. Yeah, so how we can drive continuity equation? That is the question. So the previous approach that what we have used are the finite control volume approach. Using the finite control volume approach, we have two alternative formulations. One is fixed volume approach, and another is moving volume approach. The volume also moves with the fluid as the fluid moves. And the fluid is flowing through the volume. That is the two approaches. So using this, we can find or we can compute the continuity equation. So for this, let's us consider a given area A. Look, you have a given area A, which is wedge view, arbitrarily oriented in the flow field, and flow velocity V. We have flow velocity. This area is moving with this velocity. Consider the fluid element with velocity V that passes through A. In time dt, at a small differential time t, after crossing point A, they have a moved distance v dt. So this is a moved distance s. So moved distance s is equals to what? Okay, so distance s is equals to, this is the distance s I can say here, which is v times dt. V is in meter per second, t is time, so you can get meter. So that is distance s. From here to here, it is s. This distance is s. Okay. And have swept out the shaded volume. So this is the shaded volume. So this volume, the shaded volume, is equal to the base area A times the height of the cylinder. So that is Vn times dt, where Vn is the component of velocity normal to the area A. So this is velocity, which is normal to this area. Fine, okay. So volume is equals to 1 times area. No, that is S times area. Yeah, the Vn times dt is there. So Vn times dt times A gives us the volume. Again, the mass is equals to if volume is noun, density times volume is mass. So this is volume, this is density. So mass can be computed from here. And then let m dot be the mass flow rate. So m dot is equal to dm over dt. So which is equals to the mass, total mass divided by differential time t. So dm over dt. So dm is rho v n dt a, this one. So substituting this over dt. So we can remove dt by dt. We have left rho vna. So rho va are called the mass flow rate. So density, velocity in the normal direction, and the cross-sectional area A. And this equation is called the mass flow rate equation, which is known as continuity equation. So we can find continuity equation from this relation. So the continuity equation is a product of area times density times component of flow velocity normal to the area. That is the meaning. And then we can compute the mass flux. So the mass flux is the mass flow rate per unit area. So mass flow rate is already given. That over area gives us rho VA divided by A. So A cancelled by A, you have left rho times Vn. So rho times V is called the mass flux. And the unit of mass flux is kilogram per second meter squared. So that is, so we are now apply the basic principle to the finite control volume fixed in the space case. So mass can neither create nor destroy. That is the meaning of conservation or continuity principle or conservation of mass principle. So for more elaborated case, consider a flow field where all the properties vary, that including the density also. Density vary, pressure vary, volume and velocity vary. Okay, so at time t, density rho is equal to rho of x, y, z, t, because that is one of the variable field. So in this flow field, we can consider a fixed finite control volume. So the volume is fixed and the fluid is flowing through it. This is the A approach in our previous picture. So this control volume is fixed here and the fluid is flowing through it. So it is fixed in space. dV is the differential elemental volume. You have dV, that is differential elemental volume. So this is a volume and this is surface. ds is surface actually, differential surface. And the overall surface is represented by S. Okay. So on that, net flow out of the control volume through the surface S is equals to the rate of decrease of the mass inside control value. So as I told you, in the engine, the hot combustion gases are coming from the front. Actually, air is coming from the front, fuel is added to the combustion chamber, then it is heated to the required temperature, and the hot combustion gas comes out from the combustion chamber. So that kind, the mass inside the control value continuously coming out. So the rate of decrease of mass inside the control volume. And the net mass flow out of control volume is equals to the time rate of change of mass inside control volume. That is the meaning. So let's call them the first part as B and the second part as C. B is equal to C. So what is that B? What is that C? Let's see. the elemental mass flow across the area ds is given by rho v and ds. Okay, so instead of area we use ds. So rho v ds is here now. Rho times v times ds is there. So and we can integrate it for the surface integral. So you have to be familiar with the surface integral, the volume integral, and the divergence theory of the integral. How we can convert the surface integral to volume integral using divergent theory. So you must be familiar with your mathematics course here. So this is B is the surface integral of rho v dot ds. Okay, let's take the total mass inside the control volume is rho times dv for the volume integral. It is now volume integral here. That is the total mass. Mass is equal to density times volume. So that the total mass is density times rho v, dv. So that is differential volume so the volume integral will be performed. So the time rate of decrease of mass inside the volume is a negative of the time rate of the above quantity. So minus of d dt, d over dt, that minus indicates the continuous decrease of mass. Mass is continuously decreasing. And the time rate is given. So, which is for the volume integral rho dv, which is equals to constant. And combining the above two equations, the surface integral with the volume integral, okay, which is equals to 0. So this part is the C part actually here. It is C part of our equation. Here, C, this part is B, so B is given here, C is given this, so that the combination of B and C, B is equals to C condition comes, then we can equate them. What we finally get, the volume integral of rho dv plus the surface integral of rho v dot ds is equals to 0. So that is from the conservation. So this equation is the final result of applying the physical principles of the conservation of mass to the finite control volume fixed in space. And it is called a continuity equation. So this is a continuity equation. Actually, this is general continuity equation. Simply rho v rho times v times area is equals to constant is one-dimensional approximation, or it is just one-dimensional approach. But this one is three-dimensional approach. And using this equation, so we have to change this surface integral to volume integral using some theory in your mathematics. Okay, so that helps us to get all the volume integral. Okay, so we have to apply the divergence theory here. The divergence theory for d rho dt dv here. Yeah, so the above equation also be decomposed into two parts. Okay, so this rho v dot ds in this equation means when we apply the divergence theory, it becomes this type of equation. So this is the divergence of rho v dv is in the volume integral, from surface integral to volume integral changed. So you can put the volume integral here, volume integral. Okay, so take overall volume integral from here and they equate it to dv, which is equal to 0. So for the trivial solution, actually this part dv should, integral of dv should not be 0, but we can equate rho p, d rho dt plus the divergence of rho v, which is equal to 0, gives us the continuity equation, which I earlier shown you. So this is the three-dimensional continuity equation. So d rho dt plus divergence of rho v is equals to 0. For steady flow, the rate of change of some quantity with time is 0. In the case of steady flow, d rho dt is 0. Therefore, what is left now? Divergence of rho v is equals to 0 is the continuity equation now. So this is the final form of equation, but this is an appropriate form of continuity equation. So d rho dt, divergence of rho v is equal to 0 is the continuity equation. And for steady flow, the time rate of something or any quantity becomes 0, so that the first quantity becomes 0. We have left this only. So it is divergence of rho v is equal to 0 is the continuity equation. The second one is momentum equation. Yeah, it is just a momentum equation. Can I get Nacho? Hello? Raise your hand if you are following me. Can I get Nacho? Okay, yes. So the second one is momentum equation. So we directly used the momentum equation of the Newton second law, which is force is equal to mass times acceleration, and which is the rate of change of momentum is the impulse or force. So that is the meaning. So for this, the physical principle in the case of momentum conservation principle, force is equal to the time rate of change of momentum. Force is the time rate of change of momentum. Okay, mv is momentum, p. So the time rate of change of p is called momentum. So this momentum force comes from two sources. One is the body force, and another is the surface force. So the body force is the force components, which is related to gravitational force, magnetic, electromagnetic force, and any other forces which act at a distance on the fluid inside of the volume. And when we come to the surface force, it is a pressure force and shear stress acting on the control surface. So the pressure is normal to the force, and the shear force is acting in the tangential. So these forces are the cause for momentum. So how we can equate? So let F represent the net body force, which is force per unit mass exerted on the fluid inside. So that rho FdV is the body force on the elemental volume dV. Again, the total body force exerted should be from this force only, the total body force, which is equal to volume integral of rho FdV. Okay. So the elemental surface force due to the second, another one is surface force. Look, this is body force, rho FdV, and the total body force is the volume integral of rho FdV. Again, we have surface forces. That surface force is a function of pressure, and it is a function of shear force. So in terms of pressure, the pressure acting on the elemental area ds is minus of pds. So the total pressure force is equal to minus of surface integral of pds. Therefore, now we have pressure force, viscous force is because of the shear force. So the shear effect. So force is equals to the body force rho FdV of the volume integral minus the pressure force, which is minus of PDS of the surface integral plus viscous force is the total force. So how we can equate the time rate of change of momentum of the fluid as it sweeps the fixed control volume in the sum of two terms. One is the net flow of momentum out of control volume across the surface S is equals to G. So that G is equals to the surface integral of rho V dot ds times V is that part of the volume. So another second force is the time rate of change of momentum due to unsteady fluctuation of flow properties inside the control volume, which is represented with H. So H and the G are the two things. So H is equal to G conditions will come here. No, H plus G. The total momentum, that force is equal to the dmv over dt, which is equal to G plus H is the total momentum equation. Okay, so that G plus H is comes here. So this dmv dt is directly from this force, dmv dt, which is equals to G plus H. So H is this one, G is this one, so we can equate them. Finally, what we can get overall, the time rate of volume integral rho v dv plus surface integral of rho v dot ds v, which is equal to minus of pds, the pressure component, plus the body force rho f dv plus viscous force. So this is a general momentum form of equation. So finally, the overall momentum equation is given here. Okay, it's including viscous force, including the body force, including the pressure, and so on. So this is the final form of, actually this is X component, this is final rho V. V is this V, and in equation 257, sorry, I'll represent. So this V is, it is just U in the I plus small v in the j plus w in the k. So this u is u of x, y, z, and t. V is v of x, y, z. W is w of x, y, z, t. So this is general form of equation. General form of momentum equation. So this general form of momentum equation will be resolved into x, y, and z component. For example, for the x component of the velocity and the momentum equation, what we use is the rho u. In the first volume integral, you can see rho times u. Okay, here it is rho times u, rather than rho v. Okay. So by doing that, we can resolve them x, y, z component. Applying for the y component, v, for the z component, w. So inserting those, we can consider the x, y, z component. So this is the x component of momentum, the y component of momentum, and the z component of momentum is given here. And for the above three equations, A, B, C, that equation 270A, 70B, and 70C are x, y, and z component of momentum equation. So let's consider the steady flow. For the steady flow, the time rate of some variable is 0. So that the time rate is the first part, that rho u, rho v, and rho w part are the time rate. So that is equal to 0 means what? We have left the gradient of rho W V, which is equals to minus of dP dz plus rho F2 Fz. Fz is for the Z component of force. You can see here Fx, Fy, and Fz. Viscous force Fx, Fy, Fz. Okay? Here you can see U, there V. Yeah, here U, here V, and here it is W. So that we can simplify this equation. Let's assume viscous force is 0, inside flow. Again, the body force is 0, F is equals to 0. Then this component 0, this is 0. We have left this component only. What are the components here? These are the component of force we have left only. This is one of the force. This is the time rate is 0. Considering the body force 0, considering the viscous force is 0. So here we have left this equation. And here also we have left same equation. So these are those components. This is a momentum equations. The momentum equation in the x direction, in the y direction, and in the z direction. Okay. So the momentum equation for viscous flow, which we have developed the three equations, the overall three equations are called Navier-Stokes equations. These three equations are called Navier-Stokes equations in your fluid flow analysis. These are the Navier-Stokes equations. And the simplified form of these equations, when the viscosity is 0, when the body force is 0, when the flow is steady, then we have left the simplified equations. This equation, and this one. That is called the Euler equation, the momentum equations of an inviscid flow. A steady inviscid flow is called Euler equation. So Euler and Navier-Stokes equations. So this Euler equation and Navier-Stokes equations are very fundamental in fluid flow analysis. As an engineering student, even the CFD or the computational fluid dynamics model, the software is designed based on these equations. So when you are applying the Navier-Stokes equation, you have to apply an appropriate conditions, the equations as well as the boundary conditions and the situation in which they are operating. So these are the momentum equations of the Navier-Stokes and the Euler type. I think so. The last is the energy equation. So that energy equation for incompressible flow density is considered